about 8 years of experience providing technical expertise to watershed groups. So I'm here for 3 reasons. First, to preview results from the Upper Uncompahgre water quality assessment that we've been working on for the past year or 2. And second, to share my perspective on challenges specific to watershed groups as they tackle water quality assessments. And third, to echo concerns about data interpretation mentioned by Brianna, Wendy and Joy, David, and others. So definitely a theme here. Okay, so little background. The Uncompahgre Watershed Partnership was awarded a CDPHE NonPoint source grant. The grant included funding to complete reclamation at 3 historic mine sites, water quality sampling to address data gaps, and data evaluation to prioritize future reclamation projects and to identify any additional data gaps. This is the Uncompahgre Watershed. Just under the word watershed is the town of URAY. The Canyon Creek watershed goes upstream from the large yellow line and includes the tributaries in blue and purple. And then on the other side, you have the Uncompahgre rivers. The headwaters are near Lake Como, and you have Red Mountain Creek flowing in midway through the watershed. The Uncompahgre River watershed is impaired or potentially impaired for pH, cadmium, copper, lead, manganese, silver, and zinc. So, as a refresher, you guys probably know this, but watershed management planning is an iterative process. It's a collaboration between multiple agencies and the communities. And watershed groups help the community interact with federal and state agencies, local municipalities, and industry partners, all in an effort to improve water quality and watershed health. So, as Juan mentioned, we're nonprofits that face consistent budget challenges as we try to do the most good with varied sets of resources. So this is an oversimplified picture of watersheds around the San Juans. Near the headwaters, you typically have mining impacts and natural water quality impairments, and then as you move down on some gradient that varies throughout each watershed, you go from very impaired, moderately impaired, to slightly impaired. So I just want to stress again that this is a very oversimplified diagram of what we're dealing with, but I wanted to point out the fact that reclamation should create benefits both at the site and the watershed scale. So one of the things I've been thinking in recent years is we are really good at looking at what happens immediately upstream and downstream of a site, but what about lower on this gradient? You know, we should be looking at what happens to the water quality in URAY, for instance, and how does that change through time. And in a lot of cases, our post-project data monitoring isn't very well equipped to evaluate those questions. So again, this is increased resiliency and improved watershed health. By taking a broader view, we can better evaluate whether or not we're moving the needle in the right direction in these impaired watersheds. Okay, so on to the work we've been working on recently, the Upper Uncompahgre Water Quality Assessment. The first task was compiling the water quality data, and despite the wonderful resources like CDSN and other data repositories, it's still a boatload of work to transform that data set into something that you can evaluate. Another directive on this project was to map the chemistry data to identify spatial patterns and then identify potential opportunities for reclamation and, of course, data gaps. So our water quality data set included samples collected by the UWP, the Division of Reclamation, Mining and Safety, and Water Quality Control Division from 2012 to 2017. We also pulled data from other organizations, including Riverwatch, USGS, CDPHE, the Draining Mines Inventory, and all of those data were collected from 2010 to 2017. So when it was all said and done, we had 605 samples from 100 locations. So that means just over 4,200 records for impaired or potentially impaired parameters. And that creates a real challenge when you're working on a nonprofit budget, and it becomes a balancing act. How do we take this data and turn it into information while working within the budget that we've been given? So the typical approach to do this would be to calculate a pollutant load and look at loading profiles throughout the watershed. And I know not all of you think about loading like I do every day. So I threw in this little diagram. If you have two samples with equal metal concentrations, but they occur in streams, stream A has a small flow and stream B has a large flow, you get different pollutant loads. Well, the same thing can happen year to year. If sample A was collected in a location in 2012, that netted a low load, and sample B could have been collected in 2017, a high water year that created a large load. So that was something that was really apparent in our data set, was interannual variation was making it really difficult to evaluate the success or failure of these projects simply due to variation in the flow. And you know, a lot of the observations that Brianna reported on earlier this morning were common throughout our data set. So again, year-to-year variability, high flow prevents safe access, and much of the data is collected in either June or September, like Brianna mentioned. So, and we also saw a lack of agreement, which could be attributed to either measurement error or a groundwater influence. So, that basically left us in a position where we needed an alternative assessment method or another tool to help us understand how water quality changed through time. So we did a bit of a ranking exercise. This was inspired by a USGS paper. They did a tracer study on Red Mountain Creek back in 2002, and they ranked some of their parameters. And I thought that was a really useful tool for this process, and created a cumulative scoring system for priority parameters at each location. So simple and helpful. It's something you can do fairly quickly in Excel. No sophisticated analysis necessary. So the benefits of that ranking method were first, you could quickly identify your most problematic sites and also your least problematic sites, which is really useful when you're trying to improve water quality on a watershed scale. And then we're also able to map the ranking information. So, some quick and dirty from the results. These were our top 5 most problematic sites under high and low flow conditions. So we had several audits, URAYs, Larson Brothers, and Auburn audits all ranked pretty high. But you'll notice the number of samples is low. Oh, God. Sorry about that. So at a number of these sites, we only had 1 or 2 samples. So that's an opportunity for additional investigation. And specifically, how frequently do these audits drain? Do they drain year-round or only during high or low flow? So here, the greenish dots on the map are the 20 most problematic sites out of that highest metal concentrations, that's what I mean by problematic, throughout the watershed. And a couple things were pretty telling. You know, Governor Basin, I think there's a real opportunity to do work up there and improve water quality throughout the Canyon Creek watershed. Lower Canyon Creek has, relatively speaking, better water quality, so it would be wonderful to see gains down valley. Likewise, Poughkeepsie Gulch, we saw a similar pattern. So in terms of conclusions, I challenge everyone to incorporate downstream reaches into reclamation planning and post-project evaluation. Ranking is a simple and useful tool for watershed groups to take advantage of, and it allows you to rapidly identify areas where you do more intensive water quality evaluation, can give you an opportunity to visit sites or complete other research, and maybe start with some preliminary reclamation design. So, I'd like to thank you for your time, your support of this conference and of watershed groups, and also thank you for helping me face 2 of my biggest fears, being buried alive and public speaking.